Welcome to this explainer. Okay, so today we're diving into something totally wild happening right at the edge of tech and energy. Look, if you've been tracking the global AI build-out, you already know the story. AI factories are power-hungry beasts, literally drawing as much electricity as small cities. But today, we're flipping the script. We're pulling some mind-blowing insights from the SuperMicro Innovate APAC session, specifically from experts Trent Prestigar, Kevin Kolp, and Robert Davidoff. And we're going to look at how the industry is completely reimagining energy consumption from the ground up.
So I want you to sit with this question for just a second. What if the biggest energy consumers could actually fix the power grid? Crazy, right? I mean, we hear it constantly. AI computing is draining the grid, it's pushing our utilities to the absolute brink. But what if we turn that totally upside down? What if the massive, unprecedented scale of these AI data centers is exactly what gives them the muscle to become the ultimate grid stabilizers? It sounds totally counterintuitive, I know, but stick with me, because that's exactly the puzzle we're putting together today.
Before we get too deep into the weeds, let's nail down our core concept here, the virtual power plant, or VPP. Now, throw out your mental image of concrete buildings and giant smokestacks. A virtual power plant is really just a network of decentralized units that can generate or, crucially, control power, all acting together as a single coordinated entity to stabilize the grid. Keep that phrase, power controlling units, tucked in the back of your mind, because figuring out how to dynamically control power is the absolute secret sauce for these AI data centers. All right, moving into section 1, the AI power problem. Okay, let's dive into this. When we're talking about massive GPU compute clusters, the real headache isn't just the sheer volume of power they eat up, it's how they eat it. AI workloads are incredibly, wildly dynamic. Picture this, a massive data training run kicks off, and boom, power draw spikes violently as thousands of these dense chips fire up all at once. Then, the run finishes, and the demand just drops off a cliff. It's this relentless, chaotic heartbeat of energy. And that rapid fluctuation, it puts a ridiculous amount of stress on everything, from the facility's cooling systems right up to the external utility grid. Which brings us to section 2, siloed and slow infrastructure. See, today's AI factories are facing just an overwhelming mess of complexity. First off, systems are completely siloed. The infrastructure around the chips is passive, like it watches what's happening, but can't actually do anything about it. We already know GPU demand is jumping all over the place, but the control systems are just way too slow to catch those massive spikes. There are zero unified standards for how these things should talk to each other. And honestly, the worst part? The AI factory is totally disconnected from the utility grid. Basically, the data center is flying blind, guzzling massive waves of energy with absolutely no clue what the local grid can actually handle. Now, what's really interesting here is the stark contrast. We have got to move away from these legacy silos. Right now, your building management, your power, your cooling, the GPUs, they're all living on separate islands. They literally don't speak to each other. The whole game plan here is a massive shift toward unified, standards-based communication. By leveraging modern protocols, we're talking REST APIs, Redfish, Modbus, we can finally translate all these completely different, highly technical languages into one shared standard. It's basically tearing down the walls so the entire data center can function like one giant, cohesive organism.
And that perfectly sets up section 3, enter Power Grid Manager.
The absolute game changer for all this infrastructure chaos is SuperMicro's Power Grid Manager, or PGM. You can think of PGM as the ultimate universal translator, or honestly, kind of like the master conductor of a massive, super complex orchestra. It's the central brain built to take all that fragmented, siloed mess we just talked about and orchestrate it into one sleek, coordinated platform. It sits right in the middle, continuously listening to every single component and directing traffic at literal lightning speed. So, what does PGM actually do? It actively integrates 4 crucial pillars: the utility grid outside, the core data center systems, the facility infrastructure, the heavy cooling and power delivery, and of course the GPU compute clusters themselves. For literally the first time, your physical cooling, your incoming power, the chips, and the external utility grid are all talking to each other in real time. This completely bridges the gap. It means AI factories aren't these isolated, blind energy islands anymore. Everyone's finally in the same room, speaking the exact same language. Let's look at section 4, the paradigm shift. I really want this to sink in for a second. GPU clusters are now controllable energy resources. Just wow.
Let that sit. These massive racks of servers, they aren't just hungry mouths to feed anymore. So the crucial point is, because we can now talk directly to them in real time based on exactly what the outside grid is feeling, these clusters become a lifeline. They are a dial we can actually turn up or down to instantly manipulate power availability. Literally, this one single realization just flips the entire data center industry completely on its head. And this brilliantly illustrates exactly how this works out in the real world. Okay, step one, the local utility provider, the folks running your city's power, send out a signal saying, hey, the grid is maxed out, we need power right now to avoid blackouts. Step two, that distress signal instantly hits the internal GPU power control systems through the Power Grid Manager. And step three, dynamic GPU throttling kicks in. The system literally and safely slows the GPUs down. This instantly sheds the server load, freeing up massive amounts of electricity to go rescue the local grid. And the best part? Once the crisis passes, it automatically spins right back up to full speed. It's physical, it's instant, and the whole shebang is totally automated.
Which leads us to our final stop, Section 5, the virtual power plant.
The ultimate vision here, laid out so clearly by Trent, Kevin, and Robert, is just phenomenal. The future is absolutely not isolated infrastructure. It's unified, standards-based orchestration across compute, power, and the grid. By connecting the dynamically controllable power of these massive GPU clusters directly to the heartbeat of the local utility grid, AI factories stop being these massive, problematic consumers. Instead, they become actual virtual power plants. They actively return stability to our neighborhoods, they prevent power failures, and they play a massive role in securing our shared energy future. It's a real game changer. So I want to leave you all with one final, kind of provocative thought. As artificial intelligence continues its totally relentless global scale, will our data centers be the utility grid's biggest burden or its most valuable asset? Because, as we've seen today, the tech to make them an asset, to perfectly orchestrate them into dynamic virtual power plants, is already here. It completely redefines the relationship between global computing power and energy stability. Thank you so much for hanging out with me for this explainer. I really hope it sparked your curiosity as much as it did mine. Catch you next time.